All right, now let's move on to our next definition here. This is going to tell us that if we have a curve C given by some vector function restricted to down to where t moves between a and b, and as long as it's the case that the r prime is continuous, C is traversed exactly once, then we're going to go ahead and define an arc length function of C to be equal to this. So notice I am setting up a function here. It's a function called s. So s is the arc length function. Its variable is t. And notice where t appears inside of this formula. It's this upper bound on the integral. So essentially the arc length function can be thought of as doing exactly what we did in the last example, but just saying, what if it was the case that instead of having an upper bound that was established, what if I didn't have that? What if that was yet to be determined? Could I still set up and do a full arc length calculation? Well, kind of. I should be able to do that. It's just that when I get to my answer at the end, my answer wouldn't just be a number because my upper bound at all points in time would have been a variable. So you'll note here that we choose a variable of t, and that does require that we have a different variable existing within the integral throughout. We don't want to have the same variable in our integral as we do in the upper bound. That makes it confusing when we start to do things like take derivatives and whatnot. Now, sometimes it is the case that because of this, we can rethink of the way that our arc length will be defined overall. Well, I shouldn't say how it's defined, maybe how it's notated overall. You might recall that we dealt with functions like these back in a Calc 1 class. These were functions where the upper bound was a variable. These were kind of integral functions. And there was a way to take the derivative of a function that looked like this. The way that you would take a derivative of a function that looks like this is that you would grab the formula that was on the inside of the integral and kind of pull it out. And then you would rewrite that formula exactly as it was. But instead of writing the variable of u, you would take that upper bound and you would drop it in place of that variable. Then you would have to follow up with the derivative of that variable. So like I'd have to do the derivative of t with respect to t, which in this case would simply just be a 1. And so my formula would reduce down. But if there was something more complicated up there, in Calc 1 we said we'd follow up with a chain rule. But this is what came from the fundamental theorem of calculus. So actually, if you take a look here, we could say the following. If I took the derivative of the function s with respect to t, I should just get, again, the norm of the r prime function, but just with that t dropped in place of the u. And then notice that if I took this dt and multiplied it to the other side, I should get this statement right here. What's kind of interesting is that this statement right here, this norm of r prime of t dt, is exactly what appears inside of our integral, right? So I could actually replace all of this stuff in the integral with simply ds. And so sometimes it's the case that we see that our arc length is just written as an integral from a to b of ds, meaning this differential of the arc length, okay? All right, well, we're not going to so much focus on the remark right now as we are the definition. We want to start to get comfortable utilizing this arc length function and building it. So let's take a look here at example number 2. I'm going to deal with the same helix type function that we had before over the same interval, and I just want to find the arc length function. So the first thing that I'll note here is that I don't really have to go check any conditions because I already checked them back in example 1. So I'll state that here. We already checked conditions for r of t back on example 1. So I'm not going to repeat all of that here. But now it should be really easy to find the arc length function. Notice I'm going to label it s of t, and that means I'm going to go ahead and go from 0 up to t. So again, I'm leaving that upper bound as yet to be determined. And then I'm going to go here and just do r prime of, I'll use the variable of u, du. Now fortunately, I already did a lot of this work back in the last example. Whether I refer to the variable on the inside as u or as t, I still know that I'm going to get a radical that looks like this. And I'm still going to have 4 sine squareds and 4 cosine squareds. And they're still going to be able to add up, and I'm still going to end up with an integral of square root 5. So down here, I'm going to rewrite this. This is just going to be an integral from 0 to t of the square root of 5. Notice now, I still just have my du, so when I do my antiderivative, I'm going to get root 5 times u. Then, of course, I can go ahead and evaluate this. And so what I get is root 5 times t. So I've created a function here that kind of saves me some work when coming to evaluating arc length, at least if I wanted to evaluate many different arc lengths over this interval. So let's suppose that, I want now to calculate the arc length from 0 to 1. That's super easy. If 1 is the upper bound, I can now just plug 1 into this function formula, and boom, I get that the arc length is root 5. If I want to go from 0 to 0.6, boom, plug in 0.6. If I want to go from 0 to pi over 4, boom, plug in pi over 4. So I can really quickly evaluate lots of different arc lengths and kind of avoid having to set up the actual integral and do that full calculation every time. And so this tends to be one of the big advantages of the arc length function. We're also going to see, though, that there is another advantage to doing this in the next video.